Hello everyone, this is Mayur. Today I'm going to talk about a very interesting topic in hardware and software co-design, which is trade-offs. So I'll quickly run through what I'm going to talk about in this video. First, I will give you a brief introduction of hardware and software co-design. Then I'll move on to its importance, and then I'll talk about the traditional and modern designs of hardware and software. And with this, I will move on to trade-offs in hardware and software co-design and its different types. Please note that I'm going to talk about different subtopics under each heading for better understanding of the topic. Okay, so let's start with the basic question and its answer. What are the digital systems? Digital systems are nothing but designs consists of hardware components and software programs that execute on the hardware platform. So now the question arises, what is hardware and software co-design? Hardware and software co-design is nothing but meeting system-level objectives by exploiting the synergism of hardware and software through their concurrent design. So what makes hardware and software co-design so important? Why do we need hardware and software co-design? Co-design leads to a concurrent design, which in turns reduces the time to market. So, the time to market is reduced because of co-design, as hardware and software are concurrently designed in co-design. To achieve a better design, to explore alternative designs by balancing trade-offs of specifications between hardware and software. Good design is found by balancing the hardware and software. To meet strict design constraints is very important. Power, size, timing, and performance, all these constraints are very important, and we have to meet all these constraints with our design. So for this, co-design is very important. Co-design is also important for safety and reliability and system on chip. Here I present you the two different design models, of which one is traditional and the other one is concurrent or co-design model. In the traditional design flow, we see that the hardware and software are partitioned and then they are separately designed. On the other hand, in the concurrent design flow, hardware and software is designed concurrently and is partitioned at a later stage. So, these are the two different types of design flows. Okay, so here is the general criteria on which hardware and software trade-offs are performed, keeping design constraints in mind. Criteria used for comparison of synchronous hardware designs are size, which is area, and time, which is delay. Furthermore, we can use testability, design time, and power consumption to add more value to our design. Software applications are evaluated by the amount of source code, the size of the executable code, and the necessary data size. After going through the basics for the required topic, now we move on to the main topic of our discussion, which is trade-offs. So what are trade-offs? Before knowing trade-offs, we must know what does hardware and software partitioning means, because partitioning and trade-offs are very much interrelated, and without knowing partitioning, it's very difficult to explain what is trade-offs. So hardware and software partitioning is a decision process where we decide what is to be mapped on a programmable processor, that is software, and what is going into hardware based on design constraints. The hardware-software trade-off is the establishment of the division of responsibility for performing functions between the software and firmware and hardware. We generally don't take into account firmware, so it's basically software and hardware. Okay, so here are some of the examples for better understanding of trade-offs. Trade-off between switching overhead and CPU utilization. Trade-off between simulation accuracy and simulation execution time. Trade-off between accuracy and execution time. So all these are some kind of trade-offs which could be performed to achieve a better design in our software hardware co-design. Now let's talk about different levels of trade-offs. The assembler level is defined by the instruction set of processors. Many different instruction sets are known and can be grouped, for example, into two categories, as we all know: RISC and CISC, that is reduced instruction set computing, and complex instruction set computing designs, which minimizes execution time per instruction or number of instructions per intended action. The used instructions are counted and the instruction execution time is set into relation to the frequency of use in order to define an optimal instruction set. This has generated, for example, the trend to RISC architectures, considering the hardware software co-design at this level, moving short sequences of instructions to hardware, and this can be compared with designing instruction sets. Thus, granularity of elements is fine, and the improvements may be consumed by slowing down of all instructions which RISC uses. Instruction set design is an old discipline, and now we do not expect this to be more dramatic improvement for hardware and software co-design at this level. So let's move on to the next level, which is programming language level trade-off. So it raises the level of abstraction. Next programming language have to be examined. So their constructs are implemented by sequence of machine instructions generated by the compiler. These sequences are generally larger than those which are necessary to implement complex machine instructions. So we can choose a well-known language like a C language for illustrative analysis. Its more complex construct can be grouped into 4 classes: assignment, comparison, call, and control. Starting from the software point of view, the implementation of these constructs is examined. Assigned construct can be distinguished by the assigned value, constant value, variable value, implicit given value. So the software implementation needs at least 3 cycles, whereof 2 are used for data transfers. The number of needed cycles for comparison construct depends on the types of compared values. So the type of value plays a major role here. The standard constant 0 is implemented by compiler in the same way that a user defines constant. The data transfer is generally in dominant cycle consumer. Typical cycle amounts ranges from 3 to 5 years. Function calls are also frequent in software implementations. They build the interface to software blocks used multiple times in the co-design approach. The simple control constructs, that is if then else, which we call it as, are based on compare constructs and jump instructions. Compiler optimization will eliminate the code sequences entered in case statements. The more complex control constructs define loops, for, while, do while loops. Substitution of these constructs lead to the same amount of cycles. So here first trade-off, moving software into hardware can be identified. Considerable time improvement of 4 to 30 times are achieved. It holds for one iteration of all loops in the module. Each further iteration may raise, but the number of iterations cannot be determined by source code examination because it is mostly data dependent and not known at compile time. So these are the software module level trade-offs. So we can see that the programming level trade-offs and programming language level trade-offs and the software module level trade-offs are very much interrelated, because as we design our programming language level trade-offs, in the similar way we design the software module level trade-offs, because the programming language should be compatible with the software modules we choose. Next we move on to the last type of trade-off level which we are going to discuss in our video today, which is software application level trade-off. Software application may consist of several software modules. Usually, libraries are used, especially system-dependent functions, input and output routines, only available as compiled library. We have to extend our workbench to examine also software available only as object code. On this level, only few activities can be found. A software-oriented approach to synthesize embedded controllers from C applies runtime analysis, using runtime restrictions to determine what to implement in hardware. This leads to different kind of hardware-software co-design motivation. Thus, we examined the trade-offs in hardware-software co-design at different levels. A way of comparing hardware and software design is defined. Trade-offs are found only at the software module level and above. Further research concerning the application level is underway. Design descriptions are transformed into the ISF synthesis format, which allows a more detailed examination such as synthesis. In hardware and software of larger modules and applications, additional aspects must also be considered, as for example, separation of control and arithmetic part, and the definition of module characteristics that indicate an advantageous implementation in either hardware or software. Thank you so much people for watching this video.